Look into one of the deepest images of the universe, and emptiness seems impossible. Galaxies appear almost everywhere. Spirals, glowing clouds, and distant points of light extending toward the beginning of cosmic history. And yet most of the volume inside that image contains remarkably little matter. The galaxies occupy a vast network of clusters and filaments separated by regions so underdense that the universe resembles scattered islands surrounded by an enormous dark ocean. Those islands may contain countless planets. Some may possess the chemistry and stability needed for life. But after decades of searching, humanity has still found no confirmed signal, structure, or other technological evidence from another civilization. The universe therefore confronts us with two different absences. Most of its space contains very little matter, and the matter-rich regions have produced no verified answer to our listening. Are these two silences connected? The answer is not one hidden force that removes both galaxies and civilizations. It is a deeper pattern, one that begins with gravity, narrows through biology, and ends at the limits of what any observer can detect. That silence can feel more unsettling than the darkness between galaxies. There are so many stars and so much time that company may seem almost unavoidable. If places where life could arise are numerous, why has no clear evidence of another technological civilization reached us? But the word silent carries a danger. Failing to detect something is not the same as proving that it does not exist. A receiver can miss a signal because it is too weak, too distant, directed elsewhere, transmitted at another time, or unlike anything the search was designed to recognize. In the same way, calling the universe empty does not mean that its dark regions contain absolute nothingness. Empty and silent are both comparisons, not final verdicts. Scale is the first clue. A pattern can contain countless bright objects and still devote most of its volume to the gaps around them. A galaxy can contain many possible worlds, while signals from those worlds remain separated by distance, direction, and time. In both cases, our minds notice the visible points and overlook the larger field in which those points are scattered. Yet scale is only a clue, not a solution. It can explain why abundance and absence appear together, but it cannot tell us what created the cosmic gaps or whether any world produced a signal for us to miss. The title of this investigation therefore contains a claim that cannot simply be accepted. Perhaps the universe is physically empty and technologically quiet for one underlying reason. Perhaps both impressions emerge when enormous numbers are spread across distances and times too large for intuition. Or perhaps their resemblance hides two separate stories, one governed by matter and gravity, the other by life, technology, and the limits of observation. To decide, we will have to move beyond the emotional force of darkness and silence. We must ask what astronomers actually mean when they measure emptiness, what SETI researchers mean when they report no detection, and what kind of evidence would be required to connect those results. The crowded image gives us the mystery, but not its answer. The unanswered receiver gives us an observation, but not proof of solitude. Before we can discover whether these two forms of absence share a cause, we must define exactly what is absent and what is merely beyond our present ability to see or hear. The difference begins with the word empty. In ordinary speech, an empty box contains nothing we care about. An empty road has no cars. Applied to the universe, however, that meaning becomes misleading. Astronomers do not need a region to contain absolutely nothing before calling it empty. They compare how much matter lies there with the amount expected across the universe as a whole. That larger reference level is called the cosmic mean. It is an average, not a description of every location. Matter is distributed unevenly. Some regions contain galaxies, groups, and clusters. Others contain much less than the average. When astronomers identify a vast region with a low concentration of matter and galaxies, they call it a cosmic void. The name can create the image of a clean hole cut out of space, with a sharp edge surrounding perfect nothingness. Real voids are not like that. Their boundaries can be gradual and irregular. They can contain occasional galaxies, thin gas, dark matter, radiation, and physical fields. What makes them voids is not total absence. It is their low density compared with their surroundings and with the cosmic mean. An example helps show why an average can hide extremes. If people gather in a few rooms of a building, the building may contain many people, while most rooms remain vacant. Counting everyone tells us the total, but not the pattern. Cosmic density works in a similar way, although the universe has no walls dividing one region from another. The question is not only how much matter exists, it is how that matter is arranged across volume. Dense locations can hold much of the substance, while underdense locations account for most of the space. This distinction matters because absolute nothingness is not the subject of this investigation. We are asking why matter became so unevenly distributed that enormous underdense regions came to occupy so much space. The mystery is about structure. It concerns where matter gathered, where it became scarce, and how that contrast developed over cosmic time. The word silent needs the same care. The universe does not make sound in the everyday sense across empty space, but that is not what the great silence means. Here, silence describes the absence of a confirmed technosignature, evidence that would reveal technology created beyond Earth. A technosignature is different from a sign of life. Simple organisms might change a planet without building transmitters, machines, or structures that we could recognize across interstellar distances. A living world could therefore exist while remaining technologically silent to us. Even an advanced civilization might produce evidence that our present instruments cannot detect. Every search operates within limits. A telescope observes particular parts of the sky, at particular times, with particular levels of sensitivity. A radio search listens across selected frequencies. An optical search looks for selected patterns of light. Other searches may examine different kinds of energy or unusual changes around distant objects. None can test every direction, distance, time, signal strength, or possible form of technology at once. For that reason, no confirmed detection does not mean that every possible signal has been ruled out. A transmission could be too faint by the time it reaches Earth. It could be aimed somewhere else. It could pass through our region when no suitable instrument is listening. It could use a method we do not monitor, or appear so unfamiliar that we fail to separate it from natural events. The source might also have stopped transmitting long before our search began. This does not make the silence meaningless. A null result is still a result. Each careful search can exclude certain kinds of detectable technology within a defined range. As searches improve, that excluded region can grow. But the conclusion must remain proportional to the evidence. We can say that humanity has found no confirmed extraterrestrial technosignature. We cannot turn that statement into proof that no other life or intelligence exists. The same discipline must be applied to the last part of the title, for the same reason. That phrase can carry two different claims. The stronger claim is that one identical mechanism produces both cosmic voids and technological silence. To support it, the investigation would have to show that the process which makes matter underdense also causes detectable civilizations to be absent. The weaker claim is that the two observations share a pattern. Matter might be concentrated into limited regions of space, while life, intelligence, or communication might be concentrated into limited places or periods for different reasons. The outcomes could resemble each other without having the same physical cause. That difference between a shared cause and a shared pattern will control everything that follows. A satisfying story is not enough. The connection must survive contact with what is observed, what is inferred, and what remains unknown. We now have working meanings for the title. Empty means underdense compared with a measured average, not pure nothingness. Silent means no confirmed technology detected within bounded searches, not proven solitude. The same reason remains a question about causation, not a fact already granted. Definitions, however, can only prepare the investigation. They cannot show how much of the universe is underdense, where those regions lie, or whether their arrangement follows a larger order. For that, points of light must be turned into a three-dimensional map, revealing not only where the galaxies are, but the enormous spaces between them. A picture of the night sky gives every galaxy a position, but it does not immediately tell us how far away that galaxy is. Two objects can appear close together from Earth while being separated by an enormous distance along our line of sight. To discover the true arrangement of matter, astronomers need more than a flat image. They need depth. One of the main tools for adding that depth is redshift. Light from a distant galaxy carries patterns linked to the atoms inside it. When the universe expands, those patterns are shifted toward longer, redder wavelengths. By measuring the shift and interpreting it through a cosmological model, astronomers can estimate how the galaxy fits into the expanding universe and place it within a three-dimensional survey. One galaxy provides a location, thousands reveal neighborhoods, millions begin to show geography. Each measured galaxy becomes a point in a map, and when enough points are assembled, the larger distribution appears. The result is nothing like an even cloud of lights. Galaxies gather into groups and clusters. Clusters connect through long filaments. Other galaxies trace broad sheets and walls. Between these dense features lie enormous regions where the points become sparse. Together, the bright and dark regions form what astronomers call the cosmic web. The web is not a decorative name placed over a random collection of galaxies. It describes a repeated pattern seen across large volumes. Dense nodes appear where structures meet. Filaments stretch between them. Walls form extended boundaries. Voids occupy the spaces enclosed by this network. The pattern can resemble foam, with matter gathered along surfaces and intersections, while large interiors contain much less. That comparison is helpful only to a point. Cosmic voids do not have solid walls, and the borders between one kind of structure and another are not always sharp. A galaxy distribution changes gradually. One survey may identify the edge of a void differently from another, especially when the surveys contain different kinds of galaxies or cover different ranges. This is why astronomers do not possess one perfect catalog in which every void has an unquestionable border. A void-finding method must decide what counts as sufficiently underdense, whether neighboring low-density regions belong together, and how irregular shapes should be treated. A method built around bright galaxies may describe the pattern differently from one that also includes fainter objects or uses an underlying matter model. These choices affect the number, size, and total volume assigned to voids. They explain why scientific estimates do not always produce one identical percentage. But disagreement over boundaries does not erase the larger observation. Across surveys and methods, the same broad conclusion returns. Matter is strongly concentrated, and underdense regions account for a major part of the late universe's volume. The discovery of that pattern changed the meaning of cosmic emptiness. Before large three-dimensional surveys, galaxies could be imagined as scattered more or less randomly through space, with a few obvious clusters interrupting the distribution. As more distances were measured, the gaps stopped looking like accidents between isolated groups. They emerged as organized parts of a much larger structure. The change did not arrive from one photograph. It emerged as surveys collected more galaxy positions and distances, turning samples into broader slices through space. On computer screens, each galaxy appeared as a point. At first, the points could seem crowded. Then larger forms became visible. Narrow concentrations, sweeping arcs, connected ridges, and broad areas with surprisingly few markers. The empty regions were too large and too consistently bordered by galaxies to dismiss as random gaps. Later surveys expanded the mapped volume and increased the number of measured galaxies. The web became harder to mistake for a local accident. Similar arrangements appeared in different directions and at different depths. New catalogs offered greater detail without replacing the basic picture. Some apparently empty regions gained faint resonance, while the overall contrast between dense structures and underdense interiors remained. This history matters because scientific confidence did not depend on one dramatic void. It grew through repetition. Different instruments, observing programs, and analysis methods recovered related geometry. Exact borders moved, yet the underlying fact survived. Galaxies were tracing a network rather than filling space evenly across the universe. A void, then, is not simply a place where astronomers happen to find no bright galaxy. It is recognized through its relationship with the surrounding web. Galaxies outline its edges. Nearby filaments connect into larger structures. Density falls toward its interior, although the precise shape may be uneven. The missing points form a pattern as meaningful as the points that remain. This makes cosmic maps unusual. In most maps, attention goes toward the marked locations, cities, roads, rivers, or borders. In a map of the universe, the unmarked regions carry essential information. Their sizes, shapes, and positions help reveal how matter is distributed. What appears missing becomes part of the evidence. Computer simulations provide another way to test the pattern. Starting from an early universe that is close to uniform and applying the physical model used in modern cosmology, simulations develop networks with dense structures and underdense regions. Astronomers can compare those simulated patterns with survey catalogs. The match is not perfect in every detail, and it depends on the model and the method used to identify structures. Even so, the shared web-like form shows that the observed gaps are connected to the universe's physical development, not merely to where telescopes happen to look. Survey limits still matter. A catalog may miss faint galaxies. Dust, instrument sensitivity, and target selection can affect which objects receive measurements. A survey also covers only part of the observable sky and a limited range of distances. Apparent gaps must therefore be tested to make sure they are not simply regions where observations are incomplete. Researchers address this by studying survey geometry, selection effects, and the expected number of detectable galaxies at different distances. When a region remains underdense after those limits are considered, confidence grows that the gap belongs to the universe rather than to the catalog. The resulting picture is robust without being perfectly fixed. The universe contains a connected distribution of clusters, filaments, and walls surrounding vast underdense regions. Different methods divide that structure in different ways, but none restores a uniform cosmos. The emptiness has shape. Yet a map remains a record of where matter is now. It does not tell us, by itself, why the matter moved into those arrangements. It cannot explain why some regions gained material while others fell farther below the average. The cosmic web presents the evidence and sharpens the problem. To understand why emptiness became organized, we must travel backward, to a time before galaxies, clusters, or voids existed in their present form. The web began when the universe was far smoother than it is today. The question is, how tiny early differences grew into the enormous contrast now written across the sky. To find the origin of the cosmic web, we have to imagine a universe without galaxies. There are no clusters, no filaments, and no enormous voids with recognizable borders. Matter is spread far more smoothly than it is today. Yet smooth does not mean perfectly even. From place to place, there are tiny differences in density. Those differences are small enough that they might appear unimportant. One region contains slightly more matter than the average. Another contains slightly less. Nothing in that early pattern resembles the dramatic web mapped by modern surveys. But gravity does not need a large difference to begin changing the distribution. It only needs an advantage. A slightly overdense region has a little more gravitational pull than its surroundings. Nearby matter is therefore drawn toward it slightly more strongly. As that matter arrives, the region gains mass. The added mass strengthens its pull, allowing it to attract still more material. A small initial advantage begins to grow. This is not an instant collapse. The universe is expanding, while gravity works within it, and the development unfolds across immense spans of time. Matter does not rush directly into one central point. Different overdense regions compete, merge, and influence flows around them. The original pattern contains differences on many scales, so the growing structures form a network rather than one isolated concentration. Where several flows meet, dense nodes develop. Matter also gathers along extended paths, producing filaments and broader sheets. These structures become the environments in which galaxies and clusters later appear. The web seen in modern surveys is the developed form of those early differences after gravity has amplified them. The underdense regions follow the other side of the same story. A region that begins with slightly less matter also begins with slightly weaker gravitational attraction. It cannot hold or attract surrounding material as effectively as a denser neighbor. Matter between the two responds more strongly to the overdense side. Over time, the low-density region loses matter relative to the cosmic average. It is easy to describe this by saying that gravity pushes matter out of a void, but that would give the wrong picture. Gravity remains attractive. There is no hidden repulsive force inside the young void forcing material away. Matter moves because the gravitational landscape is uneven. Denser regions pull more strongly, so flows are directed toward them and away from places where the attraction is weaker. Imagine several shallow slopes surrounding deeper valleys. An object follows the steeper path toward a deeper low point, not because the higher ground pushes it away, but because the pull toward the lower destination is stronger. The comparison is imperfect because cosmic matter, gravity, and expanding space do not behave exactly like objects on a landscape. Still, it captures the direction of the process. Concentration in one place produces relative depletion elsewhere. As matter leaves an underdense region relative to its surroundings, that region becomes even less able to resist the pattern. Its density falls farther below the average. Its interior can also expand faster relative to denser regions, where gravity slows the local separation of matter more strongly. The developing void therefore grows both emptier and larger in comparison with the structures around it. This does not mean that its contents vanish. Some matter remains. Small structures or galaxies may persist within it. The important change is contrast. Dense parts of the universe become denser, while underdense parts become more underdense relative to the evolving mean. Clustering and emptiness are therefore not separate events. Every movement of matter into a growing filament or cluster also changes the region that material leaves behind. The same attractive force that builds luminous structure helps create the appearance of emptiness across the surrounding volume. Gravity produces the web and the voids together. This answers a common puzzle. If gravity only attracts, why did it not make the universe uniformly dense? Because gravity acts on an initial distribution that was never perfectly uniform. It strengthens differences rather than erasing them. A region with extra matter gains an advantage. A region with less matter falls behind. Given enough time, a faint pattern becomes a strong contrast. The process has no preferred center. Every overdense region responds to its surroundings, while each pattern contains smaller variations inside it. Matter may first collect into concentrations, and those concentrations may become part of filaments or clusters. At the same time, neighboring underdense areas can join into larger low-density regions. Structure grows as a hierarchy, with local changes becoming parts of a wider network. This helps explain why the cosmic web is irregular. If the beginning had contained one repeating pattern, the later universe might have developed a more orderly design. Instead, the initial differences formed a complex field. Gravity followed that field, amplifying its unequal peaks and shallow regions. The resulting filaments twist, intersect, and surround voids of sizes and shapes. Expansion remains part of this history, but it must be described carefully. On the largest scale, distances between unbound regions increase as the universe expands. Within that background, gravity alters the motion of matter according to density. In overdense regions, attraction slows expansion and can eventually bind structures together. In underdense regions, weaker attraction allows matter to separate more quickly relative to the denser environment. Neither process cancels the other everywhere. Expansion does not switch gravity off, and gravity does not stop the universe from expanding as a whole. Their effects depend on scale and density. The web emerges from their combined history, with gravity turning small variations into strong physical differences inside an evolving cosmos. Computer simulations allow this explanation to be tested. Researchers begin with a model of an early universe that is almost uniform but contains small density variations. They then allow matter to evolve under gravity within an expanding cosmos. The result develops into connected dense structures surrounding large underdense regions. The precise simulated web depends on the starting conditions, the assumed contents of the universe, and the rules used to follow their evolution. It is a model, not a second observed universe. Yet its broad resemblance to galaxy surveys is important. A physical theory begins with small early variations and produces the kind of large-scale pattern that telescopes later measure. That agreement connects different forms of evidence. Measurements of the early universe indicate that small variations existed. Galaxy surveys reveal the mature web. Simulations show how gravitational growth can link the two. None of these pieces alone supplies the complete case, but together they support a consistent history. The explanation also changes what a cosmic void represents. It is not a failure of creation, a missing piece, or an empty chamber waiting to be filled. It is an evolved region whose matter history differs from that of the surrounding network. Its low-density records where matter began at a slight disadvantage and then flowed preferentially towards stronger concentrations. The web is therefore a map of amplified differences. Bright clusters mark places that gained matter. Filaments trace routes and structures along which matter concentrated. Voids mark the expanding regions left comparatively depleted. What looks like a division between something and nothing is actually a continuous physical process acting across the entire distribution. Within the standard cosmological picture, this provides a strong provisional answer to the first half of our mystery. The universe contains such enormous, empty-looking regions because gravity took tiny early inequalities and increased them. By gathering matter into a limited network, it made most of the surrounding volume sparse. But this answer applies to matter. Gravity can explain why galaxies occupy filaments and why voids grow between them. It does not tell us whether life begins easily on suitable worlds, whether intelligence commonly develops, or whether technological civilizations become visible across interstellar distances. The resemblance between physical emptiness and technological silence therefore remains unproven. Before trying to connect them, we need to understand the scale of the physical result. How much volume lies in underdense regions? How little matter remains there? Only then can we ask whether the environments capable of supporting life were concentrated in a comparable way. The cosmic web gives emptiness a shape. Measurements give it scale. Yet the numbers must be handled carefully, because several different quantities can be described by the same simple word. One question asks how much of the universe's volume belongs to voids. Depending on how researchers define their borders, which galaxies they use as tracers, and how smaller underdense regions are grouped, voids may occupy roughly 60 to 80% or more of the late universe's volume. The exact figure changes with the method, so no single percentage should be treated as a permanent border drawn through reality. The durable result is broader. Most cosmic volume is underdense. A second question asks how much matter lies within that volume. Here, the contrast reverses. Under some classifications, voids contain only around 10 to 20% of the matter, even though they occupy most of the space. Dense nodes, filaments, and walls take up much less volume while holding a much larger share of the substance. Volume fraction and mass fraction therefore describe different things. Imagine a large region divided between wide-open areas and narrow storage zones. The open areas can dominate the floor plan, while the storage zones hold nearly everything. Knowing which part is larger tells us nothing by itself about where most of the contents are kept. A third measurement concerns the density inside a typical void. Some void interiors may contain only around 10 to 20% of the cosmic mean density. Again, that range depends on what is measured and how the void is defined. A count based on bright galaxies is not identical to a measurement or model of all matter. Different voids also have different profiles. Their edges may rise towards surrounding filaments, while their central regions fall farther below the average. These measurements can sound contradictory until their roles are separated. A void can occupy a huge volume, contain a small share of total matter, and still possess a non-zero local density. None of those statements implies that every point inside it is equally empty. The average density of ordinary matter across the universe makes the contrast more tangible. Spread all baryonic matter evenly through cosmic volume, and the result would be only of the order of a fraction of a proton to roughly 1 proton in each cubic meter. This is an order of magnitude description, not a promise that every cubic meter contains one neatly placed particle. Real matter is not spread that way. A cubic meter inside a planet, a star, a cloud of gas, or the space between stars can differ enormously from the cosmic average. The average combines extremely dense objects with enormous low-density regions. It tells us how diluted ordinary matter is across the whole volume, not what an observer would encounter at every location. The distinction between ordinary matter and total matter is important. The proton comparison concerns baryonic matter, the form that makes atoms, gas, stars, planets, and living bodies. Cosmic structure also contains dark matter, which does not shine but contributes gravity. A map based on visible galaxies therefore uses luminous objects as markers of a distribution that includes material telescopes cannot see directly. This is another reason darkness cannot be translated into emptiness by appearance. A region may look black because it contains few bright galaxies, yet invisible matter still contributes to its density. Astronomers infer the distribution through the motions, clustering, and gravitational behavior of what they observe, together with the cosmological model connecting those effects. The numbers describe populations and averages, not identical parcels of space. Some voids are deeper than others. Some contain more internal structure. Some are small regions within a wider network, while others form connected underdensities. Quoted ranges compress that variety into a summary. They establish the scale of the imbalance without pretending every void follows one fixed design. A room-sized volume of ordinary air contains an immense amount of matter compared with the cosmic average. Our daily experience is built inside a dense planet, beneath an atmosphere, near a star, within a galaxy. It trains intuition on one of the exceptional places where matter has gathered. From that local viewpoint, the average universe is almost impossible to imagine correctly. But even a cosmic void is not pure absence. Dark matter remains part of its structure. Thin gas can pass through it. Radiation and physical fields are present. Some voids contain faint or isolated galaxies. Their matter is sparse, compared with the mean, and especially sparse compared with the network around them, but it has not been reduced to nothing. One of the most familiar examples of large-scale underdensity is the Bode's void. Its reported span depends on how its gradual boundaries are chosen, but it extends across hundreds of millions of light-years. That distance is difficult to convert into an everyday image. Light crossing the region would require a length of time far greater than the entire history of human civilization. The Bode's void is sometimes described using exact galaxy counts and exact numbers of galaxies supposedly expected inside it. Such comparisons can create a strong sense of scale, but they depend on survey depth, galaxy brightness, selected boundaries, and the density used as the reference. The safer conclusion is still remarkable. Across a region hundreds of millions of light-years wide, galaxies are far less common than the cosmic average would suggest. Calling it a void does not mean reaching a sharp wall and entering a perfectly empty sphere. The transition is irregular. Galaxy density declines relative to surrounding structures, and different definitions can place the edge in different locations. The example matters because it makes underdensity visible on a scale larger than familiar galactic structures, not because it provides a flawless cosmic cavity. Taken together, these measurements reveal a universe that has distributed matter with extreme inequality. Most volume belongs to low-density regions. Most matter is concentrated elsewhere. The luminous web occupies a limited share of space, but contains the structures that dominate astronomical images and ordinary accounts of the cosmos. This concentration could tempt us toward a quick explanation for the Great Silence. If most space contains little matter, perhaps most space also contains no life. In one narrow sense, that is almost unavoidable. Planets and biology require concentrated material, so empty volume cannot be counted as though every location were equally useful. Yet volume is not the same as opportunity. A small fraction of an enormous universe can still contain an enormous number of galaxies, stars, and planets. Life does not need to occupy most cosmic volume for many living worlds to exist. It only needs suitable conditions within some of the dense islands where matter gathered. Physical emptiness therefore establishes a filter on location, but it does not tell us how restrictive that filter is for life. It cannot reveal whether biology begins often, whether complex organisms are rare, or whether intelligence becomes detectable. Those questions belong to later stages of the investigation. Before reaching them, another physical change must be added. The cosmic web is not a frozen arrangement. The distances between many unbound structures continue to grow, and the expansion of the universe changes which regions can influence or communicate with one another over time. Gravity explains how matter became concentrated. Measurement shows how much volume was left underdense. Expansion now turns that spatial separation into a question about causal isolation, not merely how far apart the islands are, but whether the widening space between them can eventually place them beyond contact. The distances written into the cosmic web are not fixed. Clusters, filaments, and voids belong to an expanding universe, so the separation between many large structures changes with time. This does not mean that every object grows larger or that all distances increase in the same way. The effect depends on whether gravity and other forces hold a system together. Inside a bound structure, local attraction can overcome the general expansion. A galaxy does not simply stretch because the universe expands. Stars held within it do not drift apart in proportion to the widening distance between remote galaxies. Groups and clusters that are strongly bound can also remain together. Cosmic expansion becomes most important across the large separations between regions that are not gravitationally bound to one another. This difference between bound and unbound systems also changes how we should picture expansion. It is not best imagined as an explosion from one central location, sending every galaxy through space from the same starting point. On large scales, the distances between separated regions increase as the universe evolves. An observer in another galaxy would describe the expansion without occupying a special central seat. The cosmic web remains inside that changing geometry. Dense regions follow their local gravitational histories, while large unbound separations participate more in the expansion. Voids can grow in relative size as matter concentrates around them, but accelerated expansion is a later influence on the network's evolution. Keeping this sequence clear prevents dark energy from becoming a convenient answer for every form of cosmic emptiness. This distinction prevents two different stages of cosmic history from being confused. Gravity amplified early density differences and produced the network of dense structures and underdense voids. Expansion formed the background within which that development occurred. The web arose through their combined history, but the voids were not carved out by a mysterious late force pushing galaxies away. Dark energy enters the story through the observed acceleration of cosmic expansion. Measurements indicate that the expansion is not merely continuing. On the largest scales, it has been speeding up. Within the standard cosmological model, the unknown component associated with this acceleration accounts for roughly 68 to 70% of the universe's energy budget. That percentage can make dark energy sound well understood. It is not. Scientists can measure its apparent influence on cosmic expansion and estimate how much of the model's energy budget must be assigned to it. They do not yet know what dark energy physically is. It might behave like energy associated with empty space, but vacuum energy has not been established as its final identity. Other possibilities remain part of the scientific problem. Dark energy should therefore be treated as a name for an observed cosmological effect and the component used to describe it, not as a familiar substance flowing visibly through the voids. It is often connected with emptiness because its influence becomes especially important when matter is widely diluted. That does not mean it gathers inside cosmic voids or acts as a local wind pushing individual galaxies outward. Its large-scale consequence is clearer than its nature. If accelerated expansion continues in approximately its present form, unbound regions will separate more rapidly over time. Light can still travel between many of them now, but continued expansion changes which events can ever influence which observers. Distance alone does not automatically create a permanent barrier. Light crossing a stable distance simply requires time. In an expanding universe, however, the space separating source and observer changes during the journey. For sufficiently remote, unbound regions, the increasing separation can prevent signals sent at certain times from ever reaching us. The same limitation applies in reverse. Messages sent from our region may never reach some distant destinations. This turns cosmic emptiness into more than an arrangement of matter. The gaps between structures become part of the causal structure of the universe. Two galaxies may both exist, contain stars, and remain visible for a time, yet their future ability to exchange information can become restricted by expansion. The word isolated therefore gains several meanings. A region can be materially isolated because little matter lies nearby. It can be observationally isolated because light from surrounding structures becomes difficult or eventually impossible to receive. It can be causally isolated because no new signal sent across a widening boundary can complete the journey. These outcomes must not be projected backward as the explanation for every silence we observe today. The Milky Way belongs to a populated local cosmic environment containing many stars. Accelerated expansion across intergalactic scales does not pull its stars apart, remove its planets, or prevent signals from traveling within the galaxy. The absence of a confirmed technosignature here cannot be blamed on remote cosmic horizons. Expansion may help explain why communication across the largest scales becomes increasingly limited. It does not tell us whether another technological civilization has ever existed nearby enough to be detectable. It does not tell us how often life begins, how long intelligence survives, or what kinds of evidence technology produces. The future described here is also conditional. It depends on dark energy continuing to behave roughly as the standard model assumes. Because its nature remains unknown, scientists cannot treat every far future consequence as a directly observed fact. The acceleration is measured. The distant outcome is an extrapolation. Even with that qualification, the direction of the consequence is important. Matter began unevenly distributed. Gravity concentrated it further into islands and networks. Accelerated expansion can increase the separation between unbound parts of that structure, gradually reducing the portion of the wider universe able to exchange new information. Physical sparsity can therefore deepen into informational isolation. But this effect operates most clearly across immense intergalactic distances and future time. It cannot carry the entire explanation for the Great Silence. Before asking why no civilization has crossed the darkness with a detectable sign, we need to narrow the investigation from the empty volume to the matter-rich islands. Life cannot arise in volume alone. It needs particular arrangements of matter, energy, chemistry, and time. The next question is not how much empty space exists, but how much of the concentrated universe can become useful to life. Only then can we judge whether physical emptiness meaningfully reduces the number of places from which an intelligent signal might come. Most of the universe's volume cannot be treated as an equal field of opportunity for life. A cubic region inside a deep void and a planet orbiting a stable star are not two comparable chances waiting for biology. Life needs matter organized in particular ways. Empty volume may provide distance, but distance alone cannot build chemistry. The first restriction is physical structure. Matter must be concentrated enough to form galaxies rather than remaining thinly scattered. Galaxies gather gas, stars, and the material from which later systems can develop. They create environments where gravity brings matter together, instead of leaving it diluted across cosmic space. Even a galaxy, however, is not automatically a habitat. Much of its volume does not provide a surface, atmosphere, or setting in which complex chemistry can continue. The galaxy must produce stars, and only some stellar environments may offer suitable conditions. Around those stars, planets or other stable locations must form. The needed materials must be present, and the environment must remain usable for enough time. This creates a nested chain. Begin with all cosmic volume. Keep the regions where matter is sufficiently concentrated. Within them, keep the galaxies. Within galaxies, keep suitable stars. Around those stars, keep suitable worlds. On those worlds, keep the environments with useful chemistry, energy, and stability. Each step selects a subset of what came before. Seen this way, possible habitats occupy a restricted part of the universe's total volume. Stars themselves fill little space. Planets occupy still less. The locations where chemistry could support life form a smaller category again. The physical universe may be enormous, but biology can use only specific arrangements within it. This is the strongest defensible connection between the cosmic web and the search for life at this stage. Gravity concentrated matter into limited structures. That concentration created the places where stars and planets could exist. A universe without such structure might contain matter, yet fail to assemble the stable environments needed for complex chemistry. But concentration does not automatically imply extreme biological rarity. The small usable fraction belongs to an unimaginably large whole. Even if possible habitats occupy only a tiny part of cosmic volume, that part can still contain an enormous number of stars and planets. Observations of planets beyond our solar system have strengthened this point. Planets are not known from one exceptional system alone. They occur around other stars, and their variety shows that planet formation is a normal outcome in many stellar environments. The astronomical side of the chain therefore provides many possible locations rather than reducing the search to a handful of worlds. Possible is not the same as suitable, and suitable is not the same as inhabited. A planet may lie in a region where certain conditions could allow useful chemistry while lacking other requirements. Its atmosphere might be unsuitable. Its environment might change too quickly. A label based on location or basic physical properties cannot confirm that life exists there. The next step is even less certain. An environment that could support life may never produce it. Humanity knows that life began on Earth, but one known example cannot reveal how often the transition occurs elsewhere. Without a second known origin, the probability remains difficult to measure. The chain continues to narrow conceptually, although we do not know by how much. A world with simple life does not necessarily develop complex organisms. Complex organisms do not necessarily produce intelligence capable of technology. Intelligence does not necessarily build instruments that alter a planet in ways detectable from interstellar distances. Even technology does not guarantee a signal aimed at Earth or a lasting signature our searches could recognize. A civilization might communicate differently, remain quiet, exist briefly, or produce evidence too weak to cross the distance. Those later possibilities will matter when we examine the silence, but they cannot be estimated merely by counting planets. This is where a common argument moves too quickly. The universe contains many galaxies, therefore many stars. Many stars have planets, therefore life must be widespread. If life is widespread, intelligence must have appeared many times. If intelligence appeared, technology should be obvious. Each arrow hides a separate transition. Evidence supporting an early step does not automatically measure the next one. The reverse argument fails as well. Most cosmic volume is empty, therefore life must be rare. Voids do reduce the portion of space that can host dense systems, but the remaining web is still immense. Physical sparsity may remove useless volume from the count without reducing the number of candidate worlds to a small value. We therefore have two truths that must be held together. Habitable environments are deeply concentrated compared with the volume of the universe. Yet the concentrated matter can still provide a vast number of opportunities. Cosmic emptiness tells us where life cannot easily arise. It does not tell us what happens in the places where it can. The distinction protects the investigation from a false solution. Voids do not directly explain the great silence. They form part of the physical background that concentrates possible habitats, but the silence depends on transitions that gravity does not control by itself. The origin of life, biological development, intelligence, technology, and detectability. The physical story has brought us to the threshold of astrobiology, without crossing it through assumption. Matter had to gather before worlds could form. Worlds had to exist before life became possible. Beyond that point, the evidence becomes thinner, and the uncertainties grow. Those uncertainties make the silence more interesting, not less. If planets were extraordinarily unusual, the absence of detected technology might seem easier to understand. Instead, many possible worlds remain inside the luminous web. The question must therefore move from available places to actual searches. Humanity has listened, watched, and examined the sky for signs that nature alone may not explain. To understand what the continuing null result means, we must ask what those searches were capable of finding, and how much of the possible technological universe they have truly tested. Once possible habitats are separated from empty volume, the great silence becomes an observational question. It is no longer enough to point toward the number of stars and ask why nobody has appeared. We must ask what kind of evidence humanity has searched for, where the instruments looked, and what those searches were capable of detecting. In 1950, Enrico Fermi helped crystallize the problem with the question commonly remembered as, "Where is everybody?" The force of the question came from a contrast. The galaxy is old and contains many stars. If technological civilizations were common, long-lived, and capable of spreading or producing visible effects, why was no clear evidence already known? The question was not itself a measurement or a proof. It condensed several assumptions into one challenge. It assumed that suitable places existed, that life appeared, that intelligence developed, that technology endured, and that its effects became observable. If any link failed often enough, the expected evidence could disappear. In 1961, Frank Drake organized related factors into the equation that now bears his name. Its detailed meaning belongs to the next stage of the investigation. Here, its historical importance is enough. The question of extraterrestrial technology could be broken into parts instead of treated as one vague mystery. The practical search for evidence is commonly called SETI, the search for extraterrestrial intelligence. Yet the instruments do not detect intelligence directly. They search for technosignatures, physical signs that technology may have produced and that ordinary natural processes may not adequately explain. A radio transmission is the best-known example. Technology can create signals with features that stand out from many natural radio sources. A search can examine selected parts of the radio spectrum, looking for patterns that deserve further testing. Any candidate must be checked carefully, because human equipment, satellites, interference, and natural emissions can create misleading results. Radio is only one possibility. Optical searches can look for brief or repeated flashes of light that might be produced by powerful lasers. Infrared observations can examine unusual energy patterns that could arise if technology used and released large amounts of energy. Other investigations consider changes in a planet's atmosphere, unexpected patterns around distant objects, or possible structures and artifacts whose properties might resist a natural explanation. These categories widen the search, but they also reveal its difficulty. There is no single instrument that listens for every possible technology. Each method is sensitive to particular forms of evidence. A civilization could be obvious to one search and invisible to another. The full search space has many dimensions. First is position. A telescope observes a selected area of sky, and even a broad survey cannot watch every direction continuously. Then comes distance. A signature that is clear nearby may become undetectable farther away as its apparent strength declines. Frequency or wavelength adds another dimension. A radio receiver must examine particular ranges, while optical and infrared searches use different instruments. If a transmission lies outside the monitored range, the telescope can be pointed correctly and still miss it. Strength matters as well. A powerful beacon designed to cross interstellar space would be easier to detect than weak leakage never intended for distant listeners. Direction changes the problem again. A narrow beam aimed elsewhere might never cross Earth, even if its source were relatively nearby. Time may be just as restrictive. Some signals could continue for years. Others might last seconds or less. A telescope that watches the correct star before or after a brief event would record nothing. Repetition helps, but an intermittent signal may return on a schedule that does not match the observing program. The type of technology creates the widest uncertainty. Searches are designed around signs that humans can imagine and instruments can distinguish. A distant civilization may use methods unlike ours, produce little waste energy, communicate through channels we do not monitor, or stop using a detectable method before its signal reaches us. These limitations do not make SETI pointless. They define what a result means. When a search examines a group of stars across a stated frequency range and reaches a known sensitivity, Without finding a credible signal, it has ruled out certain transmitters under those conditions. When an optical survey finds no unexplained flashes above its detection threshold, it constrains that category of event within the times and directions observed. Scientific null results gain value from clear boundaries. They tell researchers where a particular kind of evidence was not found. Repeated searches can expand those boundaries, improve sensitivity, cover more targets, and test additional signal types. The searched region grows even when no discovery occurs. But all these bounded results cannot be combined casually into the statement that the galaxy has been fully searched. Coverage is uneven. Some directions, stars, frequencies, and times receive more attention than others. Some potential signatures can be tested with current instruments. Others remain beyond practical reach or outside established methods. One way to picture the problem is as a library of possible observations. Choosing one star opens one shelf. Selecting a frequency opens one part of that shelf. Sensitivity, direction, signal duration, and observing time narrow the selection further. A search may examine its chosen portion carefully while leaving most of the library untouched. The comparison has limits because search dimensions do not divide into neat books, and some technologies may not belong in the imagined library. Still, it explains why years of serious work can coexist with limited total coverage. Each location contains many possible signals, and each signal can appear in many ways. Improving a search, therefore, involves more than adding telescope hours. Researchers can widen frequency coverage, revisit targets, increase sensitivity, observe for different durations, or develop ways to recognize other signatures. Every improvement opens another portion of the possibility space, but none removes the need to state exactly what was tested. There is also a difference between a candidate and a confirmation. An unusual signal is not immediately evidence of extraterrestrial technology. It must be observed again when possible, compared across instruments, checked for interference, and tested against natural explanations. A claim strong enough to change our view of life in the universe demands a correspondingly strong process of verification. So far, no candidate has survived that process as a confirmed extraterrestrial technosignature. This is the solid observational core of the Great Silence. Humanity has searched in several ways for decades and has not obtained verified evidence of technology beyond Earth. The statement is important, but every added word matters. No confirmed evidence is not the same as no civilization. Searches conducted for decades are not the same as continuous coverage of the galaxy for decades. Several methods are not the same as every possible method. Silence within our detection limits is not absolute silence. The most responsible conclusion, therefore, lies between dismissal and certainty. The null result cannot be waved away as meaningless, because real regions of search space have been tested. Nor can it prove solitude, because most possible combinations of place, time, signal, strength, and technology have not been ruled out. This leaves us with a sharper version of the mystery. The question is not simply why nobody has spoken. We do not know who might speak, how they might speak, whether their signal would cross Earth, or whether we would be listening at the right moment. The deeper question concerns expectation. Why did the absence of evidence ever seem surprising? For silence to create a paradox, there must first be a strong reason to expect many detectable civilizations. That expectation cannot come from the number of stars alone. It depends on every uncertain transition between a star, a living world, an intelligent species, and a lasting visible technology. The Great Silence is therefore one side of a comparison. On one side lies a bounded null result, no confirmed technosignature. On the other lies a predicted population that may or may not have been justified. To know whether the two truly conflict, we must examine the equation built to connect them, and discover how much of it measures knowledge and how much merely gives ignorance a symbol. The great silence becomes a paradox only when it is placed beside a confident prediction. If science strongly expected thousands of visible civilizations, finding none would demand an unusual explanation. But if the expected number could reasonably be zero, the same observation would no longer be surprising. The dispute therefore begins before any telescope listens. It begins with how the expectation is built. The Drake equation was designed to organize that problem. It breaks the possible population of detectable civilizations into a chain of factors. Each factor represents a condition that must be met before a technological society can become observable. Multiply the factors together, and the result estimates how many detectable civilizations might exist at a given time. The first part concerns astronomy. Stars must form at a suitable rate. Some fraction of those stars must possess planets. Among those planetary systems, there must be worlds with conditions that could allow life. These terms describe the supply of possible locations. The later factors concern transitions that are much harder to observe. On what fraction of suitable worlds does life actually begin? On what fraction of inhabited worlds does intelligence develop? How often does intelligence produce technology that creates a detectable sign? Finally, how long does that detectable period last? The equation is useful because it prevents one large mystery from hiding its separate uncertainties. A high number of planets cannot compensate automatically for a tiny probability that life begins. Common life cannot guarantee common intelligence. Common intelligence cannot guarantee long-lived or visible technology. Every stage has a different scientific status. Astronomy has made progress on the earlier terms. Planets are known around many stars, and observations can increasingly inform estimates of how planetary systems form and how common different kinds of worlds may be. These measurements reduce some of the uncertainty that existed when the equation was first proposed. But better knowledge of planets does not extend automatically into biology. We know one world where life exists, Earth. We know one technological species capable of asking the question, ourselves. That is not enough to measure how often either outcome occurs across the wider universe. Earth shows that life can begin under at least one set of conditions. It does not tell us whether the transition is almost inevitable on a suitable planet, or so unlikely that it happened only once within an enormous region. Both possibilities must confront the same single example. The development of intelligence is similarly difficult to convert into a probability. Life on Earth produced a technological species, but the path was neither repeated independently for our observation, nor compared with another inhabited planet. We cannot treat one history as a reliable average for all living worlds. Detectable technology adds another uncertainty. A species may become intelligent without producing strong interstellar signals. It may create detectable technology for a short period, change its methods, or cease to exist. The length of the visible period can change the number of civilizations present in the equation as strongly as the rate at which they appear. This is where the equation can create an illusion of knowledge. Suppose each unknown term receives one number described as a reasonable guess. The numbers are multiplied, and a clean result appears at the end. Because the answer is numerical, it can feel measured even when several inputs were not. A point estimate hides the width of uncertainty. Saying that one transition has a particular best value does not show whether nearby values are almost equally plausible, or whether the true rate could differ by many orders of magnitude. When several uncertain factors are multiplied, their hidden ranges combine. A source of confusion is the difference between an average expectation and the outcome in one galaxy. A calculation might produce a non-zero average across many universes or repeated trials. That does not mean every case must contain that number of civilizations. When rare outcomes are involved, many cases may contain none, while a small number contains several. We cannot repeat the universe to measure that distribution. We observe one history from one location. An average must therefore be interpreted as a guide to possibilities, not as an inventory that reality is required to match. This matters when people reason that a huge number of planets makes intelligence certain. Large numbers of opportunities increase the chance of success only when the success rate is known or bounded. If the rate could be small, multiplying it by a number does not guarantee a large result. The unknown rate remains decisive. The equation exposes this dependence. Its astronomical terms tell us that the universe provides many trials. Its biological terms ask what fraction succeed. Its technological terms ask what fraction become visible and remain visible. Until those rates are measured, the size of the starting population cannot settle the count. Consider a simple chain without assigning real cosmic values. If each step succeeds often, the final outcome remains common. If only one step is extremely rare, it can reduce the entire product. If several steps are each less likely than an optimistic guess assumes, their combined effect can move the answer from many civilizations to almost none. Multiplication therefore magnifies uncertainty as well as possibility. A large number of stars enters at the beginning, but extremely small values later in the chain can outweigh that abundance. The universe can offer many trials without guaranteeing a successful technological outcome. A more honest model represents an uncertain factor as a range of possible values with different degrees of plausibility. This is called a probability distribution. Instead of declaring one fixed rate for the origin of life, for example, a distribution acknowledges that present knowledge may allow values spread across a very broad range. The same treatment can be applied to other unknown transitions. Many combinations can then be tested. Some combinations produce a galaxy containing numerous detectable civilizations. Others produce one. Others produce none. The output becomes a distribution of possible populations rather than one confident total. In 2018, Anders Sandberg, Eric Drexler, and Toby Ord used this approach to examine the Fermi paradox. They argued that common treatments of Drake-like reasoning had compressed profound scientific uncertainty into point estimates. By assigning broad distributions to poorly known factors and carrying those uncertainties through the calculation, they obtained a very different picture. Their analysis found a substantial prior probability that humanity could be alone in the Milky Way. Under parts of their modeling, even the possibility of no other intelligent life in the observable universe could not be dismissed as negligibly small. The precise probabilities depended on how the uncertain inputs were represented. That final qualification is essential. The analysis did not count civilizations. It did not observe lifeless planets across the galaxy. It did not measure the probability of life beginning or intelligence developing. It modeled what follows when current uncertainty about those events is taken seriously. The distributions themselves required informed judgment. When direct data are absent, researchers must decide which ranges deserve weight and how broadly ignorance should be represented. Different choices can shift the resulting probabilities. A model that honestly displays uncertainty is still a model. For this reason, the work should not be narrated as proof that humanity is alone. Its stronger contribution is logical. It shows that current evidence does not force a high expected number of civilizations. If scientifically plausible parameter ranges include very low values, then zero detections need not conflict with what we know. This changes the Fermi paradox. The traditional tension comes from comparing an apparently lifeless sky with an expectation that advanced civilizations should be numerous. Once the expectation becomes a broad distribution that includes zero or very small populations, the sharp contradiction weakens. Silence may be compatible with uncertainty rather than evidence of a hidden catastrophe. That does not eliminate every useful question. It does not tell us whether the origin of life is rare, whether intelligence is difficult, or whether technology usually disappears. It does not rule out civilizations that our searches missed. It simply removes the claim that some dramatic mechanism must exist because ordinary probabilities already guarantee a crowded galaxy. The difference is subtle but powerful. A solution explains why a known population is missing. Dissolving the paradox shows that the missing population was never confidently predicted. One approach searches for a cause of absence. The other audits the expectation and discovers that the surprise may have been created by unjustified precision. This also brings the documentary closer to its central comparison. Cosmic emptiness is supported by maps and physical models with strong observational foundations. Technological silence is supported as a bounded non-detection. But the proposed rarity of intelligence lies in a different evidence class. It remains a probability shaped by unknown biological and technological transitions. The physical universe became sparse because gravity amplified measured early differences. The technological universe may be sparse because one or more transitions are uncommon, but we do not know which transitions or how uncommon. The two stories cannot yet be called the same mechanism. Still, a shared pattern begins to emerge. A vast starting field does not guarantee a widely distributed outcome. Many regions of space do not contain much matter. Many planets, even if physically suitable, may not produce life, intelligence, or visible technology. Abundance at one level can be narrowed by filters at the next. The word filters here does not yet mean one specific great filter. It simply describes required transitions. We must not assume that any one of them is nearly impossible, nor that civilization destruction is the missing step. The mathematics shows where uncertainty can enter, not which history the universe chose. The local answer is therefore restrained. The Great Silence is less paradoxical than it first appeared, because the expected abundance of detectable civilizations rests on factors we cannot yet measure well. Honest uncertainty allows a galaxy with few or no detectable societies without requiring an exotic explanation. But even a correct estimate of how many civilizations arise would leave another problem. The Drake equation includes the length of the detectable period for a reason. A civilization can exist somewhere in the galaxy and remain absent from our observations if its visible phase does not overlap with ours. Counting possible civilizations treats the galaxy like a snapshot. Contact requires a timeline. The next question is not only how many technological societies appear, but whether their signals, artifacts, and periods of visibility ever share the same stretch of cosmic history as our search. A galaxy can contain more than one technological civilization and still fail to produce a meeting. The reason appears when the galaxy is viewed not as a map of stars, but as a history unfolding across time. A static map places every possible world in the same frame. It makes distant planets seem simultaneous, as though any civilization on them could look up and notice the others. Reality is different. Information cannot cross the distance instantly. Every observation arrives from the past, and the farther away the source is, the older the information we receive. A signal from another star begins a journey before it can become evidence on Earth. During that journey, its source continues to change. The civilization may grow, alter its technology, or disappear before the signal arrives. When we finally receive it, we are not seeing the civilization as it is now. We are encountering one earlier moment in its history. The same delay applies to anything transmitted from Earth. A distant observer receiving a human signal would learn about our past, not our present. Any reply would require another journey. Communication, therefore, depends not only on two civilizations existing, but on their detectable periods remaining connected across the travel time. Several conditions must align. A civilization has to arise. It must produce a signal, artifact, or planetary change that can be detected from far away. That evidence must escape its local environment or remain accessible. It must survive the distance without becoming too weak or confused with natural backgrounds. It must cross Earth or enter the field of an instrument. Finally, humanity must search at a compatible time and in a compatible way. Failure at any stage can preserve the silence. Two civilizations could live during overlapping centuries, yet use signals that never intersect. Their technologies could be detectable in principle, but too faint at their separation. One could begin searching after the other stopped transmitting. Both could exist while looking in different directions. Humanity's own technological period shows why time deserves attention. Our ability to produce signs that might be noticed across interstellar distance occupies a tiny interval compared with the ages of stars and the galaxy. This does not tell us how long another civilization remains visible. It shows only that technological detectability can begin late in a planet's history, and that our own observed example is short so far. We cannot responsibly assign one typical lifetime to every extraterrestrial society. Some may never produce strong outward signs. Some may remain detectable for a long period. Others may change methods quickly or lose the ability to create technology. With no known comparison, the distribution of technological lifetimes remains uncertain. Still, the effect of lifetime is clear. If detectable periods are long, the chance of overlap increases. Signals have more opportunities to cross another inhabited system, and observers have more time to notice them. If detectable periods are brief, many civilizations can appear at different moments without sharing a useful connection. Imagine the history of the galaxy as a dark timeline marked by narrow bands of light. Each band represents the period during which one civilization produces evidence another could recognize. If the bands overlap after signal travel is considered, detection may be possible. If they fall in separate eras, the galaxy can host several technological histories while remaining silent to each one. An experiment shows the problem. Suppose one world produces a signal after another world has ended its search. The civilization becomes visible, yet no observer remains to receive it. Elsewhere, a society listens before its neighbor develops technology. Both worlds support intelligence. Neither records the other. Add distance, and the windows must align differently. A signal sent while its makers are visible may arrive after the receiving civilization has vanished. An observer can also detect a broadcast from a society that disappeared long ago because the information continued traveling after the source became quiet. This requires no unusual physics or secret behavior. It follows from finite signal speed and changing histories. The sky is not a live display of the galaxy. It is a collection of past moments, each delivered after a journey of a length. Searching it means comparing our present with distant pasts. Distance makes the alignment harder. Signal strength generally becomes more difficult to detect as a transmission spreads or as its source appears fainter. A signal obvious near its origin may fall below an instrument's sensitivity before reaching a distant system. A powerful, deliberate beacon has a different reach from weak, unintended emissions. Direction narrows the opportunity again. A focused beam can carry energy efficiently toward a target, but the same focus leaves most other directions untouched. A civilization could transmit strong signals without illuminating Earth. Unless the beam crosses our location while we are able to observe it, its existence leaves no result in our data. Intermittent transmission creates another form of temporal sparsity. A source might emit only during certain activities, repeat on a long schedule, or produce one brief event. An instrument can point toward the correct star and monitor the correct frequency, yet miss the evidence because it listens between appearances. A civilization could also remain alive while becoming less detectable. Its communication may shift away from strong leakage. Its energy use may become more efficient or less visible. It may stop broadcasting without abandoning technology. Silence would then indicate a change in detectable behavior, not extinction. This separates civilization lifetime from techno-signature lifetime. A society might exist before it becomes visible to distant instruments and continue after one visible phase ends. The window available to SETI could be much shorter than the history of the civilization itself. Not every techno-signature has to be a temporary signal. Some artifacts could persist after their creators stop operating them. Large changes to a planet or its surroundings might remain visible longer than a broadcast. Persistent evidence would widen the period during which another observer could make a discovery. But persistence cannot be assumed. An artifact may be too small, too distant, or indistinguishable from a natural object. Planetary changes may fade or resemble natural chemistry. A long-lasting structure could exist outside the regions we examine. Permanent evidence improves the possibility of overlap only if it is detectable and recognized. The same galaxy can therefore tell different stories to observers living at different times. One society may look outward before another develops technology. A later society may receive old evidence from a civilization that no longer exists. Another may inhabit a period between detectable events and reasonably report a silent sky. This does not prove that such societies exist. It demonstrates that their existence would not automatically remove the silence. Population and detection are different questions. Even if biological uncertainty allowed several civilizations, temporal separation could keep them informationally isolated. The insight changes the meaning of the Great Silence once more. At first it appeared spatial, distant stars separated by empty space. Then it became statistical. Unknown transitions may produce few civilizations. Now it becomes temporal. Detectable technology may occupy narrow windows scattered across a history far longer than any one observer can monitor. These forms of sparsity can combine. Suitable worlds occupy selected locations. Life may begin on only some of them. Intelligence may arise on a smaller subset. Technology may become visible for part of its existence. Signals may reach only certain directions and times. Human instruments then sample a fraction of those opportunities. A populated universe could remain difficult to detect, not because everyone is deliberately hiding, but because mutual visibility requires an unusually complete alignment of place, time, technology, distance, and observation. Yet this explanation also has limits. We do not know that detectable lifetimes are short. We do not know how extraterrestrial societies communicate, whether they build persistent artifacts, or whether advanced technology becomes more visible rather than less. Temporal non-overlap is plausible, not measured. Once limited searches, uncertain biological rates, and non-overlapping timelines are included, the Great Silence no longer demands one dramatic solution. Some named explanations may still be possible, but they should be judged by evidence and testability rather than emotional power. The next step is therefore not to choose the most frightening story. It is to compare what remains: rare complex life, a great filter, short-lived technology, deliberate silence, or other forms of absence, and ask which ideas explain more than the uncertainty and detection limits already can. The Great Silence has inspired many explanations because it invites a story. A quiet galaxy can be filled with rare biology, failed civilizations, hidden observers, or technologies that have become impossible for us to notice. These ideas do not begin with equal evidence, so they should not be presented as equally strong answers. A useful explanation must first remain compatible with what is observed. Many stars and planets, one known living world, one known technological species, and no confirmed extraterrestrial technosignature. It should avoid assumptions that cannot be checked. Ideally, it should make predictions that future observations could support or weaken. There is also a question of necessity. If uncertain biological rates, limited searches, and non-overlapping technological periods already make silence unsurprising, an additional theory is not required merely to rescue the evidence. It may remain possible, but possibility is not the same as explanatory need. The first broad proposal is that complex life or intelligence is rare. Planets may be common, while the chain leading from chemistry to a technological species remains difficult. Life might begin often, but usually remains simple. Complex organisms might require unusual stability or a sequence of conditions that seldom persists. Intelligence capable of technology may represent another uncommon transition. Earth's history is compatible with such rarity because its development depended on a particular sequence of events. Yet compatibility is not measurement. We do not know which parts of that history were necessary, which were accidents, or how many different paths could lead to comparable outcomes elsewhere. The abundance of planets removes one simple version of the argument. Other worlds cannot be declared rare merely because humanity once knew only its own. But finding many planets does not establish that complex life is common. The astronomical supply of possible environments and the biological success rate remain different quantities. Rare Earth reasoning is therefore plausible at some level, but unresolved. Future observations of planetary environments and signs of biology could strengthen or weaken parts of it. For now, the silence cannot tell us whether the rare transition is the beginning of life, complex life, intelligence, or none of them. The Great Filter gives this uncertainty a more general form. Imagine the path from lifeless matter to a durable, detectable civilization as a sequence of barriers. If the universe provides many possible worlds, yet produces little visible technology, perhaps at least one barrier is extraordinarily difficult to cross. That barrier could lie behind humanity. The origin of life may be rare. Complex cells, complex organisms, intelligence, or technological capability may be unusual. If so, humanity would exist because Earth passed a difficult stage that most worlds do not. The filter could instead lie ahead. Technological societies might commonly arise, but fail to survive, expand, or remain detectable for long. This possibility gives the idea its emotional power, because the silence is then interpreted as a warning about our future. But the silence alone cannot locate a filter. It cannot distinguish a difficult biological transition behind us from a dangerous technological transition ahead. It cannot show that one sharp barrier exists rather than several moderate ones. Nor does it prove that extinction is the normal end of intelligence. The Great Filter is best treated as a framework for asking where the product of probabilities becomes small. It identifies logical possibilities, but it does not supply the missing biological measurements. Turning it into a prediction of human destruction would replace uncertainty with drama. Technological transience offers a narrower explanation. Civilizations might develop detectable technology, but remain visible for only a short period. Some could collapse or disappear. Others might survive while changing how they communicate or use energy, becoming harder for distant observers to recognize. This idea fits the timing problem. Short visible periods reduce overlap, even when civilizations arise more than once. It also avoids assuming that every society broadcasts powerful signals indefinitely. Its weakness is the absence of comparison cases. Humanity's technological history cannot establish a universal pattern. We do not know whether mature civilizations become quieter, louder, longer-lived, or more likely to create persistent artifacts. Technological transience is plausible, but its typical scale is unmeasured. Deliberate silence shifts attention from survival to choice. A civilization may decide that broadcasting is dangerous, wasteful, unnecessary, or undesirable. It may communicate only with known partners, use tightly directed signals, or conceal evidence of its presence. Individual versions of this behavior are possible. The difficulty comes when deliberate silence is used to explain the whole galaxy. Different civilizations arising in different environments and eras would need to make choices that produce the same observational result. The theory begins to depend on motives we cannot observe. Testing those motives is difficult. A future detection would refute the claim that everyone remains silent, but continued non-detection cannot easily confirm why anyone is quiet. The idea can adapt to almost any null result by saying the civilizations chose not to be seen. The zoo hypothesis goes farther. It suggests that advanced civilizations know humanity exists but deliberately avoid revealing themselves, perhaps while observing or protecting our development. This creates a clear narrative explanation for silence. Evidence is absent because it is intentionally withheld. Scientifically, the same flexibility is a weakness. The hypothesis assumes advanced observers, knowledge of Earth, shared restraint, and the ability to remain hidden. It offers few clear observations that would distinguish it from a galaxy containing no such civilizations. An explanation that can fit every possible silence without risking failure has limited testability. None of this proves that civilizations never hide or observe. It means those ideas should remain in the speculative category until they produce evidence that separates them from simpler possibilities. Other extinction or non-expansion scenarios face similar limits. A society may destroy itself, lose technology, choose not to spread, or find interstellar expansion impractical. Any one of these could happen. The Great Silence does not demonstrate that the same outcome happens everywhere. Evidence can change the ranking. A confirmed biosignature on a world would show that life began more than once, weakening claims about unique biology without settling intelligence. A technosignature would disprove solitude and any proposal that all civilizations remain undetectable. Continued null results from broader, more sensitive searches could constrain technologies more strongly. This is why testability matters. An explanation should face some observation that could count against it. Otherwise, silence can support the idea without teaching us whether it is true. A careful ranking now becomes possible. At the strongest level, we have the bounded observation, no confirmed technosignature. We also have deep uncertainty in biological and technological probabilities, incomplete searches, finite signal travel, and possible non-overlap in time. These facts and limitations already weaken the expectation of obvious civilizations. At the next level are plausible but unmeasured explanations, including rare biological transitions and short detectable lifetimes. They connect directly to unknown terms in the population problem and may become more testable as observations improve. At a weaker level are explanations built around universal motives or hidden coordination, such as deliberate galactic silence or a zoo. They are logically possible, but require more assumptions and offer fewer ways to be tested. This hierarchy does not produce a final answer about extraterrestrial life. It prevents the absence of an answer from being filled with the most dramatic available story. The silence remains evidence that must be respected, but not a blank space into which any theory can be written with equal confidence. The important result is that no exotic mechanism is presently required. A universe with few detectable civilizations is already compatible with uncertain transition rates. A universe with several civilizations can remain quiet because searches are incomplete and technological windows may not overlap. Additional hypotheses may describe reality, but the silence alone does not force them. Not required does not mean disproved. Rare complex life, filters, extinction, deliberate quiet, and hidden observers remain possibilities of different scientific strength. Their ranking can change if new evidence appears. For now, the investigation reaches a boundary. Cosmology provides a strong mechanism for physical emptiness. Astrobiology and SETI provide uncertainty, detection limits, and several unresolved explanations for technological silence. None establishes one identical cause. The title can therefore be answered only by finding a connection that does not erase these differences. If emptiness and silence share a reason, it must lie above the separate mechanisms, in the way possible outcomes become concentrated across space, biology, time, and observation. The investigation can now return to the claim hidden inside its title. The universe appears physically empty across most of its volume, and technologically silent within the limits of our searches. Are these conditions produced by the same reason? The strongest version of that claim would require one mechanism to explain both observations. The process that moved matter into filaments and clusters would also need to explain why no extraterrestrial technology has been confirmed. Nothing in the evidence supports that direct causal identity. Gravity has a well-established role in physical emptiness. The early universe contained small differences in density. Gravity amplified those differences. Regions with slightly more matter gained additional material, while underdense regions lost matter relative to their surroundings. Over time, matter became concentrated into the cosmic web, leaving most volume comparatively sparse. That explanation is physical, dynamical, and strongly connected to observation. Early variations, modern galaxy maps, and simulations form a consistent account of how the large-scale structure developed. The exact boundaries of voids depend on measurement and classification, but the mechanism does not depend on the existence of life. Technological silence belongs to a different chain. Gravity can assemble galaxies, stars, and planets. It cannot by itself determine how often chemistry becomes biology, how often life develops intelligence, or how long technology remains visible. Those steps depend on processes whose probabilities are still poorly known. The lack of a shared mechanism does not make the title useless. It changes the level at which the connection must be sought. Instead of asking whether one force causes both forms of absence, we can ask whether both reveal the same pattern. An enormous field of possibility narrowed into a much smaller set of realized outcomes. The first layer is spatial. Cosmic volume is vast, but matter does not occupy it evenly. Most matter is gathered into nodes, filaments, walls, galaxies, stars, and planets. The amount of space available is much larger than the part containing dense structures. The second layer concerns suitable environments. Not all structured matter forms galaxies. Not every location in a galaxy produces a suitable star. Not every star has a world with useful chemistry and stable conditions. Possible habitats form a subset of the matter-rich web. This does not mean that suitable worlds must be few in number. A tiny fraction of an immense total can still be enormous. The point is about distribution. Habitable possibilities are concentrated rather than spread uniformly through cosmic volume. The third layer is biological. A suitable environment is not proof of life. We do not know whether biology begins easily when conditions allow it, or whether the transition is exceptionally rare. The set of inhabited worlds may closely resemble the set of suitable worlds, or it may be far smaller. Current evidence cannot determine the difference. A fourth layer may concern complex life and intelligence. An inhabited planet does not automatically produce organisms capable of building technology. Earth proves that the transition can occur, but one history cannot reveal how frequently it occurs elsewhere. Intelligence may occupy another subset, with an unknown size. The fifth layer is technological visibility. Intelligence does not guarantee an outward sign. A society must produce technology that changes its world, releases recognizable energy, builds a lasting artifact, or sends a signal strong enough to be detected. It may remain visible for only part of its existence. The sixth layer is temporal. Even two detectable civilizations may not share a useful period. Their signals travel at finite speed. One may arise before another begins searching. A signal may arrive after the intended observer has changed or disappeared. Detectable histories can be scattered through time as well as space. The final layer belongs to observation. Humanity does not sample every possible technosignature. Searches cover selected directions, targets, wavelengths, strengths, and times. Instruments are designed around forms of evidence we know how to imagine and recognize. A real signal outside those selections can remain absent from our records. Together, these layers create what we can call layered sparsity. At each stage, a large starting set is narrowed into a smaller set relevant to the next question. Cosmic volume narrows to structured matter. Structured matter narrows to suitable environments. Suitable environments may narrow to living worlds. Living worlds may narrow to intelligence. Intelligence may narrow to detectable technology. Detectable technology narrows again to evidence that crosses our instruments at the right time. The phrase does not describe a new force. There is no layered sparsity field pushing matter, life, and signals into hiding. It is a way of organizing different mechanisms and uncertainties without pretending they are identical. That boundary is essential. A structural resemblance can guide investigation, suggest questions, and reveal assumptions. It cannot replace measurements. Where evidence ends, layered sparsity must remain an interpretation of the pattern rather than a declaration about what worlds contain. Some layers are established more strongly than others. The spatial concentration of matter has direct observational support and a successful physical explanation. The lack of a confirmed technosignature is also an observation, although bounded by search limits. The sizes of the biological layers remain unknown. We cannot yet measure the fraction of suitable worlds where life begins, the fraction of living worlds that develop intelligence, or the typical lifetime of detectable technology. Those layers are possibilities represented by uncertain models, not mapped populations. The final synthesis therefore combines different levels of confidence. It begins with a measured cosmic web, passes through observed planetary possibility, enters uncertain biology, and ends with limited technological searches. Its value lies in keeping those levels connected without confusing them. This provides the direct answer. The universe is not empty and silent because one proven process removes both matter and civilization. It is empty because gravity concentrated matter into a limited network, leaving most volume underdense. It is silent to us because detectable technology may be rare, brief, distant, differently expressed, or outside the small region of possibility that humanity has searched. They share a reason only in the broader sense that possibility is not realized uniformly. A universe can contain enormous totals while distributing meaningful outcomes unevenly. Countless locations do not guarantee matter in every region. Countless planets do not guarantee life on every world. Possible civilizations do not guarantee signals in every direction or era. The title is therefore partly true and partly a deliberate trap. It is true as a description of repeated concentration. It is false if interpreted as one physical cause. The same pattern appears across space, biology, time, and observation, but each layer follows different rules. This distinction matters because a false unification would conceal the strongest science. Claiming that voids directly silent civilizations would turn a useful comparison into unsupported causation. Claiming that gravity determines intelligence would erase the biological uncertainty at the center of SETI. Claiming that silence proves rarity would ignore incomplete searches. A qualified connection is more revealing. The universe repeatedly teaches that a large background does not guarantee a common outcome. Most volume contains little matter. Most matter is not part of a habitable planet. Most of a planet's history may contain no detectable technology. Most signals may never intersect a listener. Yet every statement after the physical layers must remain conditional. We know that matter is concentrated. We do not know that life is extremely rare. We know that no technosignature has been confirmed. We do not know whether that reflects absence, distance, timing, unfamiliar technology, or incomplete observation. Layered sparsity does not solve astrobiology. It explains why the great silence can exist without contradicting an enormous universe. The raw number of opportunities loses force when each required transition and each detection condition must also be considered. It also explains why the physical emptiness remains relevant without becoming the cause of silence. The cosmic web provides the first concentration. It determines where stars, planets, and chemistry can develop. After that foundation is built, biological and technological processes take over. The story continues from the same structured universe, but not under one governing mechanism. The scientific climax is therefore a separation followed by a synthesis. Emptiness and silence are not twins born from one cause. They are related expressions of non-uniform realization. Matter, habitats, biology, technology, and evidence become concentrated across different dimensions. This answer is less dramatic than a hidden cosmic filter that empties space and destroys civilizations. It is also more faithful to what is known. It preserves the mystery where evidence remains absent instead of filling that absence with certainty. One major consequence still lies ahead. Spatial sparsity is not finished evolving. If accelerated expansion continues, distant structures will become increasingly isolated, and information now available to observers may eventually pass beyond reach. Layered sparsity could therefore deepen with time. What begins as uneven matter and uncertain technological overlap may end as permanent causal separation between cosmic islands. To understand that future, we must ask not only why the universe looks empty now, but how much emptier it may appear to observers who come later. The universe visible may offer a temporary abundance of evidence. Across the sky, distant galaxies still reveal a cosmic web. Their light carries information about structures, events, and stages of expansion beyond our local region. If accelerated expansion continues, that access will not remain unchanged forever. Under the cosmological model, dark energy behaves approximately like a cosmological constant. Its influence does not weaken as matter becomes more diluted. On large scales, unbound regions continue separating at an accelerating rate. Nearby structures held together by gravity can follow a different future. A bound local region does not dissolve simply because the universe expands. Its galaxies and stars can remain within a shared gravitational island even as more distant, unbound structures recede. Over immense future timescales, light from galaxies becomes increasingly difficult to receive. Their wavelengths are stretched, their energy fades, and the events visible from them belong to progressively older stages of their histories. Eventually, many regions can pass beyond the boundary from which new signals will ever reach observers. Those galaxies are not necessarily destroyed when they disappear from view. They continue along their own histories beyond the accessible region. What changes is the connection. No new information crosses the widening separation. For observers inside the local island, the universe becomes observationally absent and causally unreachable. The night sky of that future could contain far less evidence of the cosmic web. The field of galaxies familiar to present astronomy would fade. Local observers might see only the structures still bound to their region, surrounded by an exterior that appears dark, empty, and unchanging. This creates a limit on knowledge. Evidence that now supports the history of cosmic expansion may become inaccessible. The arrangement of distant galaxies currently reveals large-scale structure. Their recession helps show that the universe evolves. If those tracers disappear beyond observation, future astronomers could inherit a poorer record. They might still develop powerful science from local evidence, but some conclusions obvious to us could become difficult to recover. The universe would not have lost its history. The observers would have lost access to much of the information carrying that history. Layered sparsity would then gain another level. Matter had already become concentrated into a cosmic web. Possible life was restricted to structured environments. Detectable technology required narrow conditions of time and observation. In the distant future, accelerated expansion could narrow the accessible cosmos itself. The result would be an island universe in an observational sense. A bound region surrounded by distances across which new contact is impossible. Physical space may continue far beyond the visible boundary, yet local evidence would no longer reveal it. This future should not be narrated as certain. Scientists measure accelerated expansion, but dark energy remains unexplained. The island scenario assumes that its long-term behavior stays close to the form used in the standard model. If dark energy changes, the outcome could change as well. The distinction between observation and extrapolation is essential. Accelerated expansion is part of the evidence available now. The disappearance of distant cosmic structure is a projection made by extending a model across times far beyond direct experience. Even as a conditional future, the scenario changes the meaning of cosmic silence. The quiet is not only a question of whether another civilization transmits. Expansion can eventually remove entire regions from any possible exchange. A civilization beyond the causal boundary could broadcast forever in its own region without a new signal ever arriving here. The universe can therefore become more silent to a particular observer without becoming empty of events. Information disappears from reach, not necessarily from existence. The darkness grows because connections are lost. Humanity lives before that isolation. We can still observe light from a vast range of cosmic history. We can map structures far outside our local group and test ideas using evidence that may not remain available to observers in the far future. That position does not make humanity central. It makes our observational window temporary. We occupy a period in which the wider universe remains open enough to study, while the great silence remains unresolved rather than made permanent by cosmic horizons. The final question is therefore no longer only what the emptiness and silence mean scientifically. It is what a temporary observer should make of them. We possess one known example of technological awareness, a limited search, and a sky still rich with evidence. Whatever meaning follows must respect those limits, while recognizing the unusual value of the window that remains open. The silence does not tell us that humanity is alone. It does not place Earth at the center of creation, and it does not reveal a purpose written into the universe. It tells us something narrower and more honest. Within the limits of our searches, we have found no confirmed technological presence beyond our own. That boundary matters. We know one living world, and one species capable of examining the cosmos through science. We do not know whether this is a common achievement hidden by distance and time, or an outcome so rare that much of the observable universe contains nothing comparable. Either possibility should weaken certainty rather than strengthen pride. If intelligence is common, then the silence shows how difficult connection can be. Civilizations may be separated by distance, by different eras, by incompatible technologies, or by signals that never cross the correct instrument. We may share the universe without sharing a conversation. If technological intelligence is rare, the implication is different but no less serious. The ability to understand a small part of the universe may exist in very few places. A species capable of preserving knowledge, asking questions, and recognizing its own fragility would then carry something difficult to replace. Science cannot turn that possibility into a command. No measurement of cosmic density can tell humanity what it ought to value. No failed signal search can prove a moral duty. Responsibility enters here as a human judgment, not a law of physics. Yet it is a reasonable judgment. Whether intelligence is common or rare, survival preserves the possibility of learning more. Careful observation expands the part of the technosignature landscape we have tested. Preserving a technological civilization keeps one known point of awareness from disappearing before the wider question can be answered. The proper response to the Great Silence is therefore neither to crown humanity nor to declare the universe dead. It is to admit how narrow our evidence remains. Humility means holding open more than one possibility. Responsibility means recognizing that uncertainty does not make the known example worthless. Return to the deep field image with which this journey began. It still appears crowded. Galaxies cover the darkness, each carrying histories that began long before humanity could observe them. Nothing in the image has physically changed. But its meaning has changed. The galaxies are no longer a guarantee of company. They are luminous islands inside a universe whose matter is concentrated, whose possible observers may be scattered, and whose signals must cross both distance and time. Between those islands lie physical gaps. Between their histories lie temporal gaps. Between one mind and another may lie an informational gap that no present instrument has crossed. The universe is not simply empty, and its silence is not a final answer. It is a field of separated possibilities, partly visible and largely unknown. For now, one island has learned to look with patience and care across the darkness, and to understand how much may exist beyond the reach of its light.